Hello, hello.
Alex, what's going on?
Howdy. How are things?
I haven't seen your name on screen for a while.
And indeed, that's kind of my fault. I'm sorry.
No, not your fault. It's an asynchronous class, right? A being the motivating word there. You're not supposed to be anywhere. You can be wherever you want. Like Alex
Suppose.
and John.
Hello. Hello.
I'm actually on time for once. And it's so nice to see everybody here. How's your final week going? Are you guys done yet? I mean, you're definitely not done, but class-wise, are you done yet? That feels like a small victory.
Not at all.
Really?
Yeah.
How many classes do you have today?
Not many I'm attending because it's a very busy week, but 3.
Damn. Okay, so you loaded yourself with an afternoon schedule, which is
Yes.
is great for sleeping in. But when you consider the last day of the year, you want to be done at 2:30.
Yeah.
Alzar, how about you?
I'm technically done. Well, I guess I was done with my last class, but I'm here now. So after this, I'm good for the day.
Well, this isn't a class, man. This is just
That's true.
dudes hanging out, talking math.
Exactly.
Crack open a beer. Let's talk about some weird stuff. Well, I'll give it 2 more minutes because I think 1 or 2 other people are going to show up, and then we'll get going here. We should start here. Is there anything you guys want to talk about? Is there any math thing that is perplexed that like in real life that's vexed you, or is any question you have at all about why anything works? Like in our class or any class?
The axiom talk seemed pretty interesting.
Yes, we're definitely going to get to that.
All right.
Afra and Herman, what's going on? See, I told you more people were going to show up.
Hello.
Hello, Afra. What's going on, Herman?
Yo.
This is my dream class right here. I've been dreaming of giving a lecture like this literally every single class. Not because, okay, let's be honest, I would rather give this lecture than most other lectures. Not because other lectures are bad, just because this one is so exciting to me. Because it's like a philosophical talk more than anything else. We're gonna go over a bunch of ideas, and there's no right answers really. Like I'm gonna ask you guys a bunch of questions, and I have no answers for you because at a certain point, all this stuff is made up, but it's also not. So, I think we know people. Let's go ahead and get going. So let me plug in my classic webcam here for one last.
So is it at the end everything is just theory?
Well, you know what, Afra? Let's ask ourselves that question in 45 minutes and see what's going on. To start off, though, I don't want to talk about axioms first. First, I want to talk about a proof that I didn't have time to get to, but I love and I wish I could get to. And that is a proof of something called Euler's criterion, and I think you guys might like it. So this is just a fun little appetizer here. So Euler's criterion, what that is, you guys have probably seen this before. And what that is that's if you take any 3D, this is called a convex polyhedra. And a convex polyhedra is a shape like a cube. Like I have a Rubik's Cube right here, solved, by the way, not to brag. I guess I could have just taken it out of the box that way. But the point is I have a Rubik's Cube right here. And if you count the number of faces, or let's count the number of vertices. Let's keep track of the number of vertices, the number of edges, and the number of faces. So we'll have a cube. So a cube, so vertices are its corners. So it has what? 1, 2, 3, 4 corners on top. And it has 1, 2, 3, 4 corners on the bottom. So all in all, a cube has 8 corners, 8 vertices. Now let's count the edges, the lines between the corners. So we have 1, 2, 3, 4 on the top. So that's hard to see. 1, 2, 3, 4 on the top. We have 1, 2, 3, 4 on the bottom. We also have 1, 2, 3, 4 in the middle, around like that. So we have 4 plus 4 plus 4, which is 12 edges. And then faces, we of course have 6. 1, 2, 3, 4, 5, 6 faces. 6 sides. Unless you talk to Dr. Who and say there's 7 sides, but that's not. Anyway, so the point is that's a nerd point. So there's 8 vertices, 12 edges, and 6 faces. And we can do similar things for any convex polyhedra. And a convex polyhedra, all it is a shape like this. It's a 3D shape made of like polygons. You know, you have like a polygon right here, squares. Any 3D shape made of polygons in a way that it's not like dented. It's not deflated, it's all pointing outwards. Like so, this is like a shape like this in 2D is convex. This would be concave because there's like a dent that goes in. And so we have a similar idea for 3D shapes. And so a convex polyhedra is like an undented one made of polygons like a cube. So another classic one you can have is a tetrahedron, which looks like this. Right? It's like a pyramid with a triangular base. And if we count, we have 1, 2, 3, 4 vertices. We have, let's see, 1, 2, 3, 4, 5, 6 edges. Did I count that right? Yeah, 6 edges. And we have what? 1, 2, 3, 4 faces. And I'll do one more. I think the only other 3D shape I can actually draw would be like a pyramid with a square base. So let me draw that. Something like that. And this has 1, 2, 3, 4, 5 vertices. It has 1, 2, 3, 4, 5, 6, 7, 8. Wait, 1, 2, 3, 4. Yeah, 5, 6, 7, 8 edges. And it has how many faces? 1, 2, 3.
5.
What?
5.
Thank you. 5 faces. All right.
What about the ones with triangle on top and triangle at the bottom? That shares only one.
Oh, like a triangular prism?
Yeah.
Yeah, that's fine too. Let's count those. That is, we have 1, 2, 3, 4, 5, 6 vertices. We have 1, 2, 3. Okay, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 edges. And how many faces do we have? We have 1, 2, 3, 4, 5 faces.
If we're going to do all of this, do you think we could generalize like the prisms and like the n-sided based pyramids? Because, for example, the prisms, vertices are 2 times n, where n is the number of sides for your top and bottom.
Yeah, we could totally generalize, Alex. You're right. But we're just building some examples to prove you guys a fantastic fact. And
Okay.
that is, and I'm gonna do that right now. All of these crazy shapes. I mean, they're not that crazy, I guess, but you can think of some pretty crazy ones, like the soccer ball shape. There's a bunch of them. All these crazy convex polyhedra. Let's calculate this magic thing right here. V minus E plus F. So 8 minus 12 is -4, plus 6. -4 plus 6 is 2. 4 minus 6 is -2. -2 plus 4 is 2. 5 minus 8 is -3. 5 plus -3 is 2. 6 minus 9 is -3. -3 plus 5 is 2. This should be a little mind-blowing. All of these very, very, very different shapes all have this one incredibly weird thing in common, and that is V minus E plus F always equals 2. Why? That's bizarre, right? This is called an invariant in math. And invariant in math is things that don't change no matter what you change about it. And so any convex polyhedra, no matter how many sides you add, how many whatever you add, always have this invariant thing be true. That is V minus E plus F will be 2. It's called Euler's criterion. And you can use this to do a lot of incredible things. But one thing you can do with it, I said like a Donald Trump nose breathing right there for a second. One thing you can do with it is, or what we want to do is prove it. So how would we ever go about proving this? I promise you it's actually not that hard if you know mathematical induction, which we do know. So the first thing we need to do is we need to notice that all of these shapes we just did can be called what's called planar graphs. So a planar graph we can view as planar graphs. So a planar graph is any network. So a network is like, you have some vertices, otherwise called nodes sometimes. You have some edges, right? Maybe you have this. Like this right here is a planar graph. It's a network, and what makes it planar is that it has no crossing edges. So a planar graph is a network with no crossing edges. So for example, like this right here, this right here would not be a planar graph. It also is like a devil symbol. We're going to ignore that. This would not be a planar graph because it has edges crossing here, 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 right? Now, interestingly enough, just to guys give you a little backstory, this right here would be a planar graph. You might say, oh, it has crossing edges. It does, but I mean, you can really draw anything to have crossing edges. Like we could redraw this shape to be this, to be like that, right? Like these are two like fundamentally the same shapes. All graphs care about, the only thing graphs care about are how different nodes connect to each other. And so like this graph cares that this node's connected to this and this node, for example, but it doesn't care how you angle them. And so I could angle it like this and I get a crossing edge. But that's kind of cheating because you could draw it without one. You just chose to be bad. And so same thing kind of happening here. We could have drawn this instead like that, and you wouldn't have crossing edges, which is interesting. But anyway, don't worry about that too much. The big thing you have to worry about is the fact that every convex polyhedra can be thought of as a planar graph. And so, for example, the cube, which looks like this, its planar graph is going to look like this. And I think that you can kind of see how this is a cube kind of thing. It's almost like we took this, it's almost like we took this guy and kind of smushed him into the plane, right? And you get this guy right here. Now, the thing to note that's kind of weird, and we do the same thing for the tetrahedron, which looks like this. If you smush this into the plane, you get this right here. And then if you smush like Afra's triangular prism thing into the plane, you would get like a little triangle. You get that. Yeah. So the point is, every single one of these convex polyhedra can be smushed into the plane, and it will make a planar graph. It will make this network of things with no crossing edges. And the interesting thing is, this whole property of convex polyhedra having V minus E plus F equals 2, Euler's criterion, actually holds for all planar graphs, even ones that can't be made back into shapes. And so, like, if we were to take this weird looking planar graph right here, maybe we'll do that, right? Its number of vertices is 1, 2, 3, 4, 5, 6. Its number of edges is 1, 2, 3, 4, 5, 6, 7. And its number of faces is 1, 2. But importantly, we always include the outside as a face. So it will be actually 3, because it's kind of like the faces are the number of sections that you divide the plane into. And so you divide the plane into 1, 2, 3 sections. And that's going to be 6 minus 7 is -1 plus 3 is 2. So any planar graph has this property that V minus E plus F equals 2. So if we can prove it for planar graphs, we can prove it for convex polyhedra, because convex polyhedra are just really planar graphs. If you think about it, brought up to the 3D. It's very weird. But anyway, let's talk about how you prove it. And you can prove it with induction. And here's the key thing to notice. Every single planar graph, like let's draw a weird one, can be built, like this is a weird one enough. Every single planar graph can be built from like the original planar graph, which is this guy right here. There's nothing you can really do better than this guy. I mean, I guess you could even go this guy, right? This is a planar graph, and it has what? One vertex minus 0 edges plus 1 face. That's going to be 2. So it really does work. But anyway, so if you start with this guy, notice that we can add edges to build this guy. So we'll add an edge here, 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 add an edge here, add an edge here, add an edge here, add an edge here. So every planar graph we can build up from just the dot or the barbell, whichever one you want your start to be. But we can always build up to build the planar graphs. And here is the brilliant as hell idea. We can prove that whenever you add an edge, you will not change the fact, you will not change this sum, v minus e plus f. You will not change that sum by adding an edge. That will stay the same. And this is why everything works. And so let's kind of prove this with induction. So I'll say proof by induction. Proof by, it'll be strong induction. Actually, it should be weak induction. Let's call it induction. Proof by induction. Let's go over a base case. Our base case will be this graph right here. Note this planar graph is such that v minus e plus f equals, it has 2 vertices minus 1 edge, plus we include the outside bit of the face, plus 1, which will just be 2. That's the base case holds. And then if we talk about the inductive step, so the inductive step, this is where we have to go from any old in-edge planar graph to any n plus 1 edge planar graph you can build from that. And if we can show that this whole v minus e plus f equals 2 thing will hold through every single step of adding an edge, well then clearly any planar graph you build has to have that v minus e plus f equal 2 hold. Because every time you add an edge, it holds, it holds, it holds until you get your new graph. So let's say, so we want to show that any n plus 1 edged planar graph built from any n edged planar graph will built from any n edge planar graph will preserve the sum v minus e plus f, which I'll write in red because it's important. We'll preserve the sum v minus e plus f. All right, so let's go ahead and consider any n plus 1, or consider any n edged planar graph. Assume v minus e plus f equals 2. So let's just draw a weird one, right? So we could have a planar graph like this. This would be fine, like this. Now, consider any n plus 1 edged planar graph built from this. So by built from this, I mean, let's consider adding any edge to this graph to give it n plus 1 edges. So this is just any, you can just imagine it's any graph, and we're just assuming v minus e plus f equals 2. We even know it's 2 yet. We're just assuming it is 2. If we add an edge, let's say we add an edge here, right? So this is going to be our new edge. If we do it that way, if we add edge actually, let's do a different one first. Between two existing vertices, what happens? So when we add an edge to this graph, we can either do it between two existing vertices, like here and here, or like here and here, or like here and here, or here and here, or we can do it like kind of out straight on its own. So let's first consider if we do it between two existing vertices.
We would get a new face, right?
We would get
And
a new
edge.
If we add it between two existing vertices, let's see what happens. If we add between two existing vertices, v stays the same. We don't get any more new edges. E goes up by 1, since we added a new edge, and F goes up by 1, since this one face we had here is now two faces. And this will happen anywhere we add this edge. If we add it here, we just split this. There used to be one face there, now there's 1, 2. If we add it, you know, like, yeah, it doesn't matter where you add it. You always split one face into two faces. So the number of F goes up by 1. There's one face, there's now 2. So then if we look at our sum here, then we have, so for our new graph, we get V minus, and then E, but we had to add one edge, plus F, but again, we add one edge. Then our faces went up by 1. Which, if you work it out, the V minus E, so we add this new edge we added here, and this new face we added, this minus 1 and this 1 cancel out. So we just give V minus E plus F, which we assume to be 2. The point is that this sum equal 2 going in, if you add an edge between any two existing vertices, then V minus E, the new sum will still be 2. Or yeah, we still equal 2. And so we have one more case to contend with, and that is, what if we add, okay, what if we build from this by adding an edge not between existing vertices. So if we do it not between existing vertices, that's like making a stray one out here. Then notice our number of vertices has to go up by 1, because we have to put 1 at the end of this new edge. Then V goes up by 1. And then we add in an edge, so E goes up by 1. E goes up by 1. And finally, faces, we don't make any new faces here, right? We had an outside face here, and we have a thing poking into it, but we didn't split it. So that outside face is still just one outside face. And so, and F stays the same. So again, in our new setup, we have V, but now we have to add 1. So this new edge, as V, you got to add 1. Minus the number of edges you had previously, but plus 1. We have a new edge. And then plus the number of faces you had previously, because the number of faces didn't change. And again, this plus 1 here and this minus 1 here will cancel. So you still get this B minus E plus F like you had before, which is 2. And that's the proof. You can't see that, my bad. But that's what I just wrote right there. But that's induction. This is how powerful induction is. We just proved that if you add any edge, right? Like basically what we just proved is that let's say we're trying to prove it works for the cube. So we know the cube, its planar graph looks like this. We know the cube planar graph looks like this. So you start off with this guy. We proved in the base case this has v minus e plus f equal 2. Now if we add this edge, we proved if you add an edge, if you add any edge to a planar graph, it's still going to have v minus e plus f equal 2. It started with that. So since the barbell here had v minus e plus f equal 2, this new graph will have v minus e plus f equal 2. Add an edge, we preserve v minus e plus f equal 2. Add an edge, we preserve v minus e plus f equal 2. Preserve it, preserve it, preserve it, preserve it, preserve it, preserve it, preserve it. So because this graph right here, because this blue graph right here had v minus e plus f equal 2, this whole thing must preserve that. This must also have v minus e plus f equal 2. So every graph you possibly make, every planar graph will always have v minus e plus f equal 2. And because, and this is kind of a subtler point that I didn't prove to you guys, but because you can always smush convex polyhedra into the plane to get planar graphs, this means that every single convex polyhedra is going to have v minus e plus f equals 2. And that really wasn't that hard of a proof. It was all from induction. I mean, that's kind of cool, right? Come on, give me something.
So I guess the follow-up question is kind of like, what is it about concave polyhedra that makes it so you can't smush it into a planar graph?
Ooh. That's
right,
a good question,
because this kind of depends on like this observation that indeed all convex polyhedra go into this nice kind of other type of data type that we know more about. But why can't we transform concave ones into this?
That is such a good question that I don't know the answer to. I think I come up with a counterexample though. Imagine if we had a shape. This drawing might be terrible. That was basically like two tetrahedrons stacked on each other, like in an hourglass kind of way. Like this. Let's see if it works for this guy. So here we have our number of vertices is 1, 2, 3, 4, 5, 6, 7. We have our number of edges is 1, 2, 3, 4, 5, 6, 7, 8, 9. Wait, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, nice, 12. Then our faces is 1, 2, 3, 4, 5, 6, 7. Wait, 1, 2, 3, 4, 5, 6, 7, 8. So here we get 7 minus 12 is 5, or sorry, negative 5. Plus 8 is 3, not 2. So it definitely doesn't work for this. And you can kind of see why. And this is almost cheating a little bit because we just connected. We just like both these tetrahedrons by themselves would have v minus e plus f equal 2. But here we kind of connected their vertex to like share a vertex. And so that's going to screw everything up.
But I have a question.
Yeah.
You put the top triangle in the bottom, so we only have like one less surface. Does that work right now? We get a 2 if we do that?
I'm sorry, what should I do?
Like if we put triangle on top and triangle at the bottom and no surface.
Oh, are you saying if we do like, you have this and then nothing in between?
No. Like, should be a triangle on top and triangle at the bottom.
Like this?
Looks like a diamond shape. Like just to the top triangle of the last diagram.
So you could connect to tetrahedra by the faces rather than by the vertex.
Oh, sorry. Thank you.
Thank you.
So we start with this, and then we connect Yeah. Oh yeah. No, this is totally fine. This is called there's a word for this. It's like, well, actually, is this? Yeah, yeah. And so this will work, right? This is a convex polyhedra. We can smush it into the plane and be fine. Yeah.
Okay, but
we
quick
only-
question then.
Yeah.
Is that couldn't you have something that has the same planar graph, except you have it where like you have a tetrahedron inside of a that counts as like a negative inside of another tetrahedron?
I think. Oh.
So like you've carved out a tetrahedron's worth out of
Yeah,
a
well,
separate bigger tetrahedron.
But let's talk about this. Imagine if you had like a house shape.
Okay, this is probably a nicer way to do it. Yeah.
So imagine if you had like a house shape like this. So you have like a pyramid on top. You know what I mean? So something like that, right? So you have a nice house shape like this. This is a totally convex polyhedron. It totally work. We have what? 1, 2, 3. Well, we'll have the same number. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices. We have 1, 2. So we have 9. We have 1, 2, 3, 4. Sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 edges. 9 faces. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. Wait. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, yeah. So this is going to be 18 minus 16, which is 2. It's totally fine. But now let's think about if we did the same shape, but instead of having this pyramid pointing out, we kind of pushed it in. If we push that pyramid in, we'd get, so we have a cube. We have a cube right here, but now we have this like negative pyramid pointing in, right? And so this negative pyramid pointing in, will this have the same properties is the question. Yeah, it totally would. Yeah.
But it's a dented shape, right?
But
So what exactly is a concave polyhedra?
So this is a concave polyhedra because it's dented, but it happens to still follow Euler's criterion. So it's not so much that, so this is not an if and only if. So if you're a convex polyhedra, you'll satisfy Euler's criterion. If you're not a convex polyhedra, you still might, but you're not guaranteed to, because you run into weird situations like this.
Okay, but like in a sense, this
guy will have the same planar graph. Really, what it comes down to is that if you can be smushed into the plane and form a planar graph, there's a way to do this rigorously, like actual mathematically. But if, like smush is doing a lot of work here. But if you can smush something into the plane, make a planar graph, like these two will have the same, then you will follow Euler's criterion. But this one can't be. Otherwise,
right.
It doesn't. So this guy can't follow Euler's criterion. I mean, you can kind of see why, because if you tried to smush it, I mean, you have a tetrahedron, but then you have another one on top. So then you would need like another tetrahedron here.
And you'd need to connect both of the center points to each other, right?
So it would be like that, and it'd be a whole thing. It would be like that, and then there's no way you can manipulate this to be planar, to have edges not crossed. Anyway, though, I mean, this is fast. This is how math works, right? It works for convex polyhedra, really, because it works for any planar graph. So anything that we made in a planar graph, it works, but not every concave polyhedra can be. Some can, not every. Anyway, though, that's just what I think is like one of the most fun induction proofs to do, because it proves something that, like if you were just told like b minus c plus f equals 2, prove it. Like, where do you start? But if you're a little clever, you got it. Now let's get into talking about any more questions on that we want to talk about. I mean, we don't have to talk about anything today. But, yeah.
So like, how do you convince yourself that every convex polyhedra can be turned into a planar graph?
That's an excellent question. And I'll be honest, I don't really fully understand that either.
And okay, is this a graph theory thing or is this like a topology thing?
Graph theory for sure.
Okay.
It's totally a graph theory thing.
Despite all the smushing.
Despite all the smushing, yes. Yeah. How could you convince yourself?
Like if we go to like the general case of
there are reasons to suspect it'll work, because there's whole things you can do with. So we'll go over this and we'll talk about axioms real quick. I was going to tell you there's things you can do, and that is, imagine you have any convex polyhedra, right? And then like here's a corner of it. Like these all go out and they do their own thing, and maybe it looks like this, and it goes like whatever it is. But let's just focus on this corner of it right here. And now let's think about the angles here. Right? Let's think about like the angles here, A, B, C, and D. Do we know anything about these angles is the question.
The sum has to be, I think, strictly less than 360.
Yes. The sum has to be strictly less than 360 degrees. And so when you're dealing with convex polyhedra, you have things like the sum is strictly less than 360 degrees. You also have things, you know, where it's like, okay, if I have certain shapes here, which is how you can prove actually. Well, okay, yeah, now. But you also know things where it's like, if you have a polyhedron like this, you know the formula for like the number of sides and how it interacts with the angle that's going to be here. Because what's the whole thing? A square is 360, a triangle's 180. So the number of sides minus 2.
Minus 2 times triangle internal, so 180, right?
Yeah, times 180. 180 times n minus 2, region degrees. That gives us the formula for the number of total, the sum of all the angles, interior angles of an insided polygon. And then, you know, you have to divide that by
And to get like the average for the regular.
Yeah, you get some stuff. The point being, all of this restricts convex polyhedra in such a way that I think that comes out to being able to prove that when you smush it down, you'll be able to move the lines around in a way that they won't cross. I'm not sure though. I'm really not sure. It's a fantastic question. It's actually fun to look up some of the planar graphs for like really weird shapes. Like, let's share screen. So let's do planar graphs for a planar graph for dodecahedron. Yeah, so I mean, this is the way to draw that. It's pretty wild. Like, really, the way I think about it is, if you look at like a dodecahedron, and then you think about taking like, so you have like a front face and like a back face. Think about taking that back face and expanding it out and around to almost turn the thing inside out. And then when you look at it that way, well, everything's got to lay out in the plane. Does that make any sense? It makes sense to me. I don't know if it makes sense to anybody else.
Yeah,
So,
it's like a skirt of 5 pentagons and another skirt of 5 pentagons, and then there's the big pentagon.
So for the cube, you take the cube like this, and imagine, so this will be, the red will be your front face and the orange will be your back face. So imagine this is your front face, and imagine taking this orange guy and then kind of almost unfurling it around like this. So unfurling it around like this, almost turning it inside out, right? And so it's going to be expanding this back part, and then it's going to go inside out. So you'll get the blue will show up here, the green will fly up here, the yellow will fly up here, the white will fly down here, and the orange will kind of still be in the back. The orange will kind of still be in the back, but smushed down or whatever, which is why the face is added. It's the whole thing. And when you do that, to me, that makes sense, but that's not really a mathematical proof. Anyway, though, that's a good question, Alex. Yeah, clearly it all relies on that. But either way, we did just prove all planar graphs have E minus E plus F equal 2, which is still cool on its own. But now let's talk about axioms. And so just further conversation we'll get into it. So this whole time and all the class we've done, right? I have constantly said on your homework, it's like, why? Why is that true? Why does that work? All that kind of stuff, right? And because I'm annoying, but also because there's usually reasons why things work. For example, you know, if you add, like in some of our classic even odd proofs, we'll end up with like 2 times k plus t or whatever, and you go, oh, because k and t are integers, you know, and the integers are closed under addition, k plus t is an integer. The point being, like, when you add 2 integers, there's a reason you get an integer, and that's because the integers are closed under addition. And so everything you kind of keep asking why. And in the real world, right, if you're a kid, you go like, Daddy, why is the sky blue? Well, my dad was just like, because it is, move on. But the point is, like you could entertain that and go, oh, the sky's blue because the sun pumps in white light with photons or whatever. White light's made of all different types of light, and then the atmosphere scatters that light, and the shorter length blue ones are able to the longer length red ones kind of get through, the shorter length blue ones get scattered, and that goes all around and creates blue ambient light or whatever. Why do blue waves get scattered? Blah, blah, blah. Like, why does the guys see blue? You can keep asking why, and eventually you'll get down to like, because photons and then muons and whatever, particle physics, quantum mechanics, and then you'll eventually reach a wall where you're like, we don't know. For science, at least, you eventually reach a wall. Math, you can do the same thing. You keep asking why, and you also reach a wall, but you don't reach a wall of we don't know. You reach a wall of because we assumed. And that wall of because we assumed, the thing that everything else in math is built on is the axioms. The axioms are the original assumptions of math. And I say original, not to mean they've been here forever. It's just that every piece of math you've ever done in your life has been based on the axioms. So there's kind of there's 2 stories here. There's number 1, the math, the axioms. The other story is the people and human beings and how we do math. And they're two equally interesting stories, I think. Let's just look at the axioms first, and you'll see how basic they are and kind of how incredible they are. So let's share my screen here. I'll show you Wikipedia so you believe me. Let's go ZF axioms. But they're called the ZF axioms because they're named after these 2 mathematicians. One guy named Zermelo and one guy named Frankel. So they're the ZF axioms. And then there's also the ZFC axioms, and we'll see what those are in a second. But anyway, here are there's 9 axioms. That's right. I've been saying 7 to 8. There's 8 to 9, my bad. And we'll go over a possible 10th one. So these are all the axioms. These are the things we assume to be true, and they're all based in set theory. Because you won't see a number show up here at all, because actually everything comes down to sets in math. Set theory is the foundation of everything, which is fascinating, why I spent a whole 6 days on it. But anyway, so number 1 here is the axiom of extensionality. And that says if x and y have the same elements, then x equals y. Actually, this will be fun. I'm going to just write down the axioms that we're going to talk about, and we're going to see why they mean what they mean. So I'm right here too. So let's see here. So the first axiom says, in a very complicated fashion, it says that, let's use a more fun color for this. It says that for all x, for all y, for all y, for all z, z in x, if and only if z in y, this implies x equals y. Actually, I'm going to change y and x to a and b. So a, b, let's change it to this. This implies A equals B. So this is the most basic axiom you could possibly think of. And let's look at what it means. So it says remember, everything here is sets basically. It says for all sets A and B, and for any element, if this element is in A and this element is in B, then we say A equals B. Well, actually, we really want this. Yeah. So, but this is exactly what it means for two sets to be equal. Sets are equal if they have the exact same elements, and that's all this is saying. This is saying that we say two sets are equal if and only if we say two sets are equal if every single element in A is also in B, and vice versa. This is just the first axiom. This is the first assumption of mathematics. So sets are equal if they have the same elements. Sets are equal if they have the same elements. Now let's go for 2. So 2 says, this is a weird one. For all x, for all A, such that A does not equal the empty set, or A is not equal to this empty set, this implies there exists a x, there exists x in A such that this is going to be weird. X intersect A equals the empty set. So let's go through what we're saying here. What we're saying here is that for any set A, if it's not the empty set, then there has to be an element in A. That's the first part. Then like for all sets A, if A is not empty, there's just an element in A. Super obvious, right? This is the things math are based on, these kind of assumptions. Because before you had this assumption, well, how did you know that was true? But then it also has a different part, and it says X is not only in A, it's in A such that X intersect A equals the empty set. And here's the point behind that. If X intersect A did not equal the empty set, that would mean X intersect X and A had some things in common, but X is inside A. And there's a big problem in math with putting a set inside of itself. That ends up breaking everything. If you put a set inside itself, you are destined for logical paradoxes. And so we just ban it from the very beginning. And we say that can't happen. We say if you are a set and you're not empty, then you have an element that doesn't contain yourself. Because a classic example of where this goes wrong, right, is imagine S equals the set of all sets that don't contain themselves. So S is the set of all sets that don't contain themselves. And so, for example, like if you made a set A equal to 1, 2, A, or whatever, that would contain itself. That would not be that would not be a good thing. But anyway, let's not S be the set of all sets that don't contain themselves. And the question is,
is S an S?
Yeah, is S an element of S? Let's go through the options. If S is an element of S, so if S is in this weird set that we define with the sets that don't contain themselves, if S is an element of S, that would mean, thus, by definition of S does not contain itself. Thus, S not an S, contradiction. However, let's look at what if S was not an S? Well, then S does not contain itself. So S is an S. By definition, contradiction. Do you see the problem? If we build this set of all sets that don't contain themselves, the question of where S goes is a paradox. It both can't be an S and it can't not be an S. And remember, we want sets to be binary. Sets are these things that they either do or don't contain every element. And so it has to either contain or not contain S, but it can't do either. Math breaks down. And this is called being inconsistent. So there's two big properties of an axiomatic system. An axiomatic system is any set of axioms. Because what we do is we're going to use these axioms and we're going to put them together to build new things. We can use these non-axioms to build the natural numbers. We can use the natural numbers to build the rational numbers. We can use the rational numbers to build the real numbers, build the complex numbers, right? Everything comes back to the sets. Everything in math is built from these axioms. And an axiomatic system being consistent, that means they will never, ever contradict, right? This would be a contradiction right here. And so the way we get rid of this contradiction is with number 2 right here, which kind of guarantees you can't contain yourself, and so you have nice things happen.
So that whole thing is called Russell's paradox, right? That whole.
I believe so. Yes, Urban. Yeah.
I was reading that while you can get around it by just saying, oh, it doesn't contain itself. That was not really. It's starting to be clear that it wasn't sufficient enough. Like there was other issues that crop up with just saying that. Do you know anything about that? Yeah, that's where the reading stopped. I was like,
I wish I did, man. So here's what I can tell you. So what I can tell you is so axiomatic system being consistent is one where you'll never have a contradiction like this, right? You'll never be working with like 2 of these axioms and get to one conclusion, and then work with another axiom and get to an opposite conclusion. This will never happen if the axiomatic system is consistent. And the ZF system Zermelo-Fraenkel axioms have been proven to be consistent. So they won't ever contradict each other. So I think maybe was what they're getting at there is that I think the system we have right now is consistent, but they might be saying that it's kind of painting with too broad of a brush, that maybe we're cutting out too many sets that we'd really like to keep just because we're afraid of this inconsistency popping up. And maybe there's a better number 2 axiom that'll have like a finer, be like a scalpel rather than an axe, and let us allow more sets.
So we'd like more completeness, basically.
Exactly. So the other half of consistency is completeness, and that is the ability to prove any question you ask. And here's the thing. Well, let's just do like one more axiom real quick, and then like there's 9 of these, and they're all basic like this. They're all basic like this. There's an axiom of power sets. There's a well-ordering theorem. There's so many things like this. All of these axioms, there's 3, 4, 5, 6, 7, 8, 9. You have all the tools you need basically to read all of them now. Like we're just what we've done in this class. You could go through and read all these axioms and really try to understand what they mean. The point is we have these really 8 axioms here, right? And they, like I said, build all of math. And so one thing we can actually do with this, which is interesting, is I'll show you how you build the natural numbers. So here's the way you build the natural numbers. It's crazy. You can build it from sets. It's called the piano construction. You're welcome, Herman. Thanks for coming. So it's called the piano construction. It goes like this. So the real question is, how the heck would you Like the natural numbers, that's been the bedrock of our class. Like any property of the natural numbers, you're allowed to assume, but they're not the bedrock of actual math. They don't show up anywhere in the axioms, meaning they have to be built from things using the axioms. So how would you build the natural numbers? And here's the real insight to have. The insight to have is about the bijection things that we barely mentioned at the end of class last time. And that is, like, really, right? Like if we have the set 1, 2, 3, we can show it as the same size as the set A, B, C, just by showing there's a bijection between the elements. A bijection being we can pair the elements up. So we can pair them up and go, okay, we have 1 with A, we'll pair 2 with B, or sorry, 2 with C, and we'll pair 3 with B, right? We can pair them up in this way. And if you think about it, if you can pair, if you have 2 sets of things, and you can pair all of them up in a way that none are left over on either side, then you have to have the same amount of both of them. Like I think I did this last time. If I have a group of pins, a group of markers here, and I have a group of pins here, you could ask the question, do I have more markers or more pins? And you start by going, let's say I had this right here. You start by going, okay, I'll pair these off. I'll pair these off. I'll pair these off. All my pins are gone. There's a marker left over. Therefore, there kind of has to be more markers than pins. Or it could be the other way around, right? Like if we had this, well, then we could pair all the markers off. We can pair the pins. There's more pins than markers. But if we have, if we started with you know, these groups and these groups, right? You could pair them up like this. And notice now you've paired up every marker, you paired up every pin, there's none left over on the other side. Therefore, really there has to be the exact same amount in both. This captures the idea of number that we have. So fundamentally, 2 things having the same size just means that you can form a bijection between them. You can pair them off with none left over on the other side. That's what a bijection is. All right. So really then, what's it mean? What does 3 mean? Well, 3, right, is really anything that can be put in bijection with this. It's any possible set that you can pair off with this amount of pins would be called, we'd say there's 3 of them. So really, 3, we say there's 3 of something only if we can form a bijection between those things and another set of something that we just defined to be 3. And the things we define to be 3 go like follows. So really what I'm saying here is that if you can define a set to have 1 element, or you can define a set to have 2 elements, or you can define a set to have 3 elements or 4 elements, once you can make one of those sets, you just say 4 is just the size of anything you put in bijection with those, which is interesting. But anyway, so the way you do that is you start off with nothing, because in math, we kind of have nothing to start out with. Like this whole time we've been talking about sets, right? But sets of what? The axioms have no numbers. They have no nothing. So what would we make sets of?
Sets of sets.
The only thing we have starting out in math is the empty set. The set of nothing. That's the only thing we have. The brilliant idea, though, this is the exact same thing that Indian mathematicians did, the Hindu mathematicians did back in the day, is before them, basically, no culture had a number or really a firm concept of 0. They had a number for 1, a number of 2, a number for 3, but you know, you could say, oh, there's 3 lions, but if there was nothing out there, you wouldn't go, oh, there's 0 lions. You just be like, there's no lions. You wouldn't think to put a word to that concept of nothing, but the Hindus did. It turned to be amazing. Same thing here. Here we have the empty set, right, which is just nothing. But if we give it a name, it becomes something, and that's incredible. So we give it a name right here, and we say, and so we say this, like, so this would kind of correspond with 0. And then we consider the set of the empty set, because the empty set is a thing, so we can put it in a set. So there you go. And then we can consider, okay, what if we take our first thing in our sequence here, and our second thing in the sequence and make a set of that. And then you say, what if I take the set of everything I've developed in my sequence so far? And you can keep going like this. You can keep going, right? At each time, you just take all the things you have so far and put them in a set. All the things you have so far, put them in a set. All the things you have so far, put them in a set. And when you do that, right, we call anything, we basically consider this to be 1. We consider this to be 0. We consider this to be 2. We consider this to be 3. We have things a little more complicated than that, but the point is this is where the numbers come from. Like 3 is a nice little name we give it, but if you look under the hood, it really represents a set like this or anything you can put in bijection with a set like this, anything you pair off like this. This is where numbers come from. This is where everything comes from.
Why is it 3 and not 4?
So if you look at the commas, Afra, that's the important part. There's actually only 3 elements here. There's this empty set, the set of the empty set, and this set right here. We have this, this, and this. Because the empty set, remember, is really just this. But yeah, so if you think about it, right, we could have rewritten this as, well, this we consider to basically be 0, this we basically consider to be 1, and this we basically consider to be 2. And I think that makes it look more obvious. It's confusing with all the curly braces. But anyway, this is where numbers and everything come from. Everything comes from these axioms that you just combine logically. And then this whole question of like, oh, well, wait a minute. How do I know I can keep doing this forever? That's an axiom. There's an axiom that says that you can keep doing this forever. It just says it, right? It doesn't mean, it does not, and this is the big key part of the conversation that Afra asked in the very beginning. And that is, so it's all theoretical. Yes and no. So it's all made up in the sense that it's all made up by human beings. Like we decided what the axioms were. But here's the key to math. I really think of it like a hard fantasy story. So if you guys ever like watch like Avatar: The Last Airbender, or you watch some good like movie story, usually like sci-fi fantasy, something like that, right? They usually establish rules to the universe. And in my opinion, a good show, a good story sticks to those rules. Where you'll have things where it's like, oh, a waterbender can bend anything with water, therefore they can bend blood or whatever. Like that sticks within the rules or whatever. Things like that. That's what math is. The axioms are the rules of the universe. And then all the math after that is just playing with those. All math after that is just things that follow. It's things that must happen from that. It's like I'm trying to think of other good examples, but I think this kind of I keep going back to Avatar: The Last Airbender because it's a great show. But the point is, this is kind of how this is what axioms are. The rules of the universe, the set of everything that's going on. Now the question is, does that make them made up? And the answer is they can be, because we could make up different axioms. We could make up whatever axioms we wanted to, and we could still talk about what would happen then, right? This is why do you guys know, what's his name? Terrence Howard, the actor that played Rhodey in the first Iron Man movie. He's kind of crazy. And he has this theory that 1 × 1 = 2. And apparently he really sticks by this. He really, really believes 1 × 1 = 2. He goes, how can 1 × 1 = 1? It makes no sense. 1 × 1 has to equal 2. And so he believes that all of mathematics is a fraud because we all believe a nonsensical thing that 1 × 1 = 1, right? Here's the thing he doesn't understand. Well, first of all, he doesn't understand 1 × 1 = 1. He doesn't get that. But the second thing he doesn't understand is we can look at that. Let's just assume 1 × 1 = 2, and you can play with that. And we already know what that is. You get a system that's like a mod system. It's a whole weird thing. But the point is, mathematicians have done that. We've done a lot of things. We can play with these ideas of what your starting point is. So why do we care about these axioms in particular? The reason we care about these axioms in particular is because of the people behind math. And this is the thing that's kind of the other story here. Math did not always have axioms. So the first axiomatic system we really know about is the Greeks and their geometry, Euclid's Elements. If you guys remember geometry class went a lot like this class. There's a lot of proofs where you go like, oh, because of this, this happens. Because of this, this happens. Because of this, this happens. And
isn't it all theorems?
what?
Geometry is all theorem based.
Yeah, it's all theorems, but it starts with axioms or postulates. It starts with a group of things that you assume, and everything else is built from that. And those things you assume are pretty dang basic things. They're basically things that say like, if A equals B and B equals C, then A equals B, A equals C. Things like that. So pretty basic stuff. And that was key. But for the rest of math outside of geometry, we didn't have axioms for the longest time. The axioms weren't really created until like the late 1800s, maybe the early 1900s. And like a lot of math took place between them. Like, have you ever heard of Newton? Ever heard of Leibniz? Ever heard of Euler? Like all of these people worked without axioms. And so how they know things were right? Well, they just kind of were like, yeah, that makes sense, right? That's the whole deal. They're just kind of like, yeah, this makes sense, so we're going to say it's true, basically.
I mean, the physicists at least had like experimental evidence to back them up, right? So.
Well, that's exactly what I was going to get at. So it made sense to us with our meat brains that live in this 3D physical universe, right? And so we kind of use our universe as a template for truth, which is a kind of an interesting thing in the sense that in our universe, if you take like one ruler, right? If ruler A and ruler B have the same length, and ruler B and ruler C are the same length, then ruler A and ruler C are gonna have the same length. That's just gonna happen. It doesn't have to happen though. Like this is where things get really weird. Like we assume that to be true in math because it's true in our universe, but we could work with a mathematical system where that doesn't happen. Because, well, really, at the end of the day, why does that happen? That's a really deep question of like, why does the transitive property work? And there is no answer. We just assume it does in math, and we observe that it does in the universe, but there's really no inherent reason why it has to work. You could imagine systems where it doesn't work. So for the longest time, people work without axioms until eventually people started contradicting each other. People started getting contradictory results, and they realized it's because they started with contradictory assumptions. They started with different assumptions. And so at some point, this led to a total breakdown in math. People panicked, and they were like, oh my God, I spent my whole life on this. Is it actually meaningless? Does it mean nothing? And luckily, the answer is no. They just had to sort out all the assumptions, all the axioms, and there was debates over exactly what to put in and all that kind of stuff. And they eventually settled on these 9 ZF axioms and one more ZFC called the axiom of choice, which is weird. I wish we had time to talk about it, but we don't. The axiom of choice, some people choose to use it, some people don't choose to use it, but it's kind of a controversial axiom because really all it says at the end of the day, the axiom of choice says that if you give any set, it's okay, you can take an element for one. Like a lot of times we say like, okay, let X be an integer, or let X be a rational number or something like that, right? That's kind of axiom of choicey. We're saying, okay, we just have one. But we don't construct it. A less axiom of choice thing to do would be to say, okay, because X is a rational number, we know it can equal A over B, where A is an integer, B is an integer. You kind of construct it, whereas axiom of choice just says, yeah, you can just say you have one. And that leads to weird things, apparently, where you can actually like take two spheres, you take a sphere and you can break it up into finite pieces and put it back together into 2 different spheres that have the same size. Whole weird thing. That's called the Banach-Tarski paradox. That's not really a paradox, it just works. That's why people don't like axiom of choice, because you get weird things like that. But, it kind of makes sense. So the point being is that we eventually had to come up with these axioms to be the foundation of mathematics. But we wanted these axioms to fit with the mathematics that was done so far. And the mathematics that was done so far was all just about what made sense to us with our meat brains in the universe. So you guys have everything you need to know, and you can make a decision now about math and axioms and meaning, basically. Like, because we made up the axioms, does that make them meaningless? In a certain sense, doesn't that mean everything's meaningless? Like what's not made up, kind of. I mean, our axioms are based on our physical world and kind of how we think things work, right? So there is some basis for them, but there doesn't have to be. And I'll leave you guys with that. Yeah, that is math. At the end of the day, when you keep asking why, you hit the axioms. And the question is, by hitting the axioms, does that mean everything is meaningless? Or do we give it meaning? You know what I mean? It's kind of like when, like I kind of said that calling something zero gives it meaning and gives it power. Calling the empty set something gives it meaning and gives it power. Is just making up a system, does that give it power in and of itself? Or is it all meaningless? And the big problem is that we need these axioms to deal with infinities, because almost everything else, like for example, if I made the claim that if you add any two even numbers less than 100 together, you'll get another even number. So the evens are closed under addition as long as less than 100. We could just straight up check that. We wouldn't need to do any real complicated math. We could just straight up go, okay, 2 plus 2 is 4. 2 plus 4 is 6. 2 plus 6, whatever. 4 plus 6 is 10. You could go through and you could check all the like 10,000 possibilities, whatever it would be. And you go through and make sure it all works. But once you start dealing with infinities, things change, because we have no way to physically verify infinities. So it's kind of like, even if you wanted to base your math fully on the physical world, you would not be able to talk about infinities. You'd never be able to prove that every even number plus every even number will always be an even number. Inherently, in order to do that, you need to make some assumptions about how infinity works, because it doesn't exist in our real world. You have to assume it works this way and stick very strictly to those assumptions, very logically, rigorously to those assumptions, like it's our favorite story, our favorite fantasy story. We don't want to have any plot holes or whatever. We want everything to be consistent. But yeah, that's what's going down. We need axioms to talk about infinities. And infinities are like what makes math amazing. And infinities allow us to do integrals and derivatives and things like that. And integrals and derivatives allow us to do calculus. And calculus allows us to do all the crazy things we have, in the real world. Like, so that's it. I mean, what do you guys, I mean, Phil, like, what do you guys think?
The fundamentals are a little shaky at this point. It seems like everything is made up, like literally made up by the theories we have in our mind. Like, for example, if I saw something, I said, okay, that's fine. That's I can have 4 edges to it. Okay, fine, I'll keep it that way. It's just like how people thought.
So it is made up. But the important thing to notice is that while the rules of the universe are made up, the things we do with them are not. In the sense that, like, all of math we can check. We can go like, okay, this is true because this is true because this is true because this is true because the axiom says so. But it comes back down to the axioms, but it has to fit together. It all has to logically work together. But at the end of the day, it is made up at the foundation. So maybe that means it's nothing. But the weird thing is, like there's that quote that says like math is unreasonably effective at describing the universe, which I actually don't really like that quote, because math is essentially just the study of patterns at a certain point, the study of how axioms form patterns. And inherently, if the universe had any patterns in it, it would be described by math. So it obviously would be true. But the point is, I mean, from a certain perspective, like these rules that we made up, Afra, seem to have very useful things in the real world. You know what I mean? So it's like, if that's any test of them, then maybe it's not that arbitrary. John, were you gonna say something?
I was just gonna say how annoying it is that math boils down to just like philosophy and not actual real provable things. But no,
Yeah,
it does make sense.
So the good news is it's not provable, but it is verifiable. In the sense that if you give me any proof, I can tell you if it's true given the axioms of Zermelo-Fraenkel, the Zermelo-Fraenkel axiom. So I can't verify it, but that it's only as true as the axioms are. But this raises an excellent question. And that is, this is the one no one wants to hear. What even is truth? at the end of the day. And I don't mean this in like a fake news kind of way. I mean this in a way of we go, okay, well, we made the axioms up. But at a certain point, what's it mean for anything to be true? For example, and this raises a really interesting question. And this is a very incredible thing. A guy named Gödel had an amazing theorem. I think it's still probably my favorite theorem in math. I love it. I don't really understand it, but I want to. And it's called the incompleteness theorem. And what that says, it says that no axiomatic system that contains the natural numbers will be both, and Alfred, we'll get to your stuff later, I'm sorry. No axiomatic system that contains the natural numbers will be both consistent and complete. What that means is if your system has the natural numbers, which we really want it to, then either it's not going to be consistent when you're going to have contradictions, or it's not going to be complete. You can't have both. But not being complete means you can't answer every question you can ask. And we're in that situation. We chose an axiomatic system that, as humans, we chose an axiomatic system that is consistent because we hate contradictions, but we also like the natural numbers, meaning inherently our system is incomplete, meaning there are questions you can ask that don't have an answer. And that's weird. Like, for example, and we don't know what they are. Like, we know some exist, but we don't know all of what they are. So
this is just an article of some guy, it's like a programmer who was explaining Gödel's incompleteness through like a Lisp type of perspective.
that's awesome. Yeah.
And it was pretty good, and I think it would be fun to read for some people.
Yeah, I'm going to check this out after this. The point is, though, this means that there's some problems that mathematicians have been working on their entire lives that might be this way. The twin prime conjecture is a really famous one. The twin prime conjecture says twin primes are primes that are apart by 2. So like 3 and 5 are apart by 2, 5 and 7 are apart by 2, 11 and 13, 17, 19, those kind of things. The 29, 31, those. The twin prime conjecture says that there's infinitely many of those. It's possible that's one of those things that we can't answer. That literally, no matter how you put the axioms together, no matter how long your proof is, it like this just falls through the cracks. This statement just cannot connect to them in any way. And so the question is, if you have a statement that doesn't connect to the axioms, what's the truth of that statement even mean? Like, does that mean it's like could it, like, can it be true and we just can't prove it? Can it be false? We just can't prove it? Well, it can't really be false, I don't think, because if it was, well, yeah, I guess it could be false. Yeah, like how would you, like, yeah, like how do you even wrap your mind around that? Like, is it true? Is it false? Or does true and false even mean anything at this point? Like this is the realm we're in. But yeah, that we're I mean, I'll say we're over time. I know this is required. This is all just us talking about math. So the point is, I don't know what the point is. Like this is all where you guys can decide what to believe. But I hope you guys now have some knowledge going forth about what all this is based off of. And so, in a certain sense, I want you to know that math is, in a certain sense, I want you to know it's not made up, because it all comes down to the axioms. We can prove everything works. But once you get to the axioms, it is made up. So on a shallow level, I want you to know it's not made up. On a deep level, I want you to know at the end of the day, it is made up. But you know, what isn't made up? Is it a problem? Who knows?
I literally recently, like last Thursday, learned about all these in one of my other classes. Like that was STS class, and he gave us a list of things that we talked about that day. And the end part was incompleteness theorem, which was discovered in the early 20th century.
Yep. That screwed people. That really screwed people. They thought that meant that people up because they thought every question could be answered because it feels like it should be able to. Like the idea that there's infinitely many twin primes, for example.
But this also gave people that some things might not be complete. It's like halfway through and we can just leave it that way. Yeah.
I mean, that's the bummer part about it. It not only said that our system's incomplete, it said any system you could possibly be incomplete. And that's crazy. Another one one that's actually this that you can maybe wrap your mind around is that we've briefly talked about very, very shortly, like the last 2 minutes of last class, we don't have any time, sadly. But the natural numbers are infinitely large, and the real numbers are infinitely large. The real numbers are larger than the natural numbers. There's, in a certain sense, more real numbers than natural numbers, because if you try to pair them up, like I was doing with the pins and the markers, if you try to pair them up, there will always be real numbers left over. You can never pair them up in a way where you capture every single real number. So there's more real numbers than natural numbers. Here's the question. Is there any set between the naturals and the real numbers? Is there any set that's too big to be paired with the natural numbers, but too small to be paired with the real numbers? And the answer is, this is one of those questions. It kind of all comes down to whether or not you accept the axiom of choice. If you accept the axiom of choice, I think the answer is yes, you can make these sets. If you don't, the answer is no. Or maybe the other way around. It's called the continuum hypothesis. By the way, the point is, depending on which axiom you accept, changes your answer. It's equivalent. But that's kind of bizarre. Like, what's the answer? It feels like there should be an answer. It feels like, yes, a set should exist, or no, a set shouldn't exist, but we don't know. So, I don't know. I'm going to call it a day here, people, unless anyone has anything else to add. But the point is, this is where we're at. It all spirals down. And this is actually, if you read the book Alice in Wonderland, that was written by a guy named Lewis Carroll, or that's his pen name. I forget what his actual name was, but he was a mathematician back in the day. He was a mathematician back in the day when these ideas were first starting to be developed. These ideas of like, let's break free from physics a little bit and talk about, like, what if we consider a system that works like this? What if we consider a system that works like this? And he hated it. He hated all this kind of abstract, this more abstract thinking about these ideas. And Alice in the Wonderland is like is largely, a lot of that is a subtle diss track to modern math, because like all the weird stuff that happens is like a bunch of things that are analogous to like actual math theorems of the day that he thought were ridiculous and shouldn't be allowed. And so he created a world where those things actually worked physically and showed how stupid it would be. But anyway, something like that. They're like I'm gonna say it's exactly like that. It's also just a good book, but you know what I mean. But anyway, yeah. So go forth, everybody.